हेलो एवरीवन। आज हम इस वीडियो लेक्चर में केमिकल प्रॉपर्टीज ऑफ फिनोल्स के बारे में डिस्कस करेंगे। तो स्टार्टिंग विद द केमिकल प्रॉपर्टीज ऑफ फिनोल्स। सो दिस रिएक्शन इन्वॉल्व्स ब्रेकिंग ऑफ CO bond or breaking of OH bond similar to that of alcohols. So first we'll take up various types of reactions involving breaking of OH bond or CO bond. So heading is chemical properties of phenols. So first of all we'll take up acidic nature of phenols. Phenols are more acidic than alcohol. So let's see why phenols are more acidic than alcohols. So we have this phenol. Now phenol being acidic in nature, this releases H plus ion in solution when this gives you phenoxide ion. These phenoxide ion is resonance stabilized So because of the conjugate base phenoxide ion being resonance stabilized, phenol is acidic in nature, whereas same resonance was not possible in case of alkoxide ions. So phenols are more acidic than alcohol. So the reason is the phenoxide ion, that is the conjugate base coming from this acid phenol, is more stabilized due to resonance. So we have this. So this is the resonance stabilization. So this is the reason why phenols are more acidic than alcohol. So therefore, this phenol being more acidic than alcohol, these phenols react with sodium hydroxide or potassium hydroxide when this gives you sodium salt of phenol plus H2O, whereas the corresponding reaction of alcohol was not feasible, does not give this reaction. So this proves if phenol is more acidic than alcohols. The reason is here, phenoxide ion is more resonance stabilized, whereas alkoxide ion cannot be stabilized by resonance. Now these phenols, the acidic nature of phenol is not very acidic, this is very weakly acidic. Now this being a very weak acid, this does not react with sodium bicarbonate, no reaction takes place. So the reason is sodium bicarbonate is a weak base, so this weak base cannot react with a weak acid to give you strong acid, that is carbonic acid. So this is very weak base. So now look at this. Though phenol reacts with sodium hydroxide or potassium hydroxide, but phenols does not react with sodium bicarbonate. So the reason is this is a weak base, this is also weak acid. So weak acid, weak base cannot react to give you strong base and strong acid. but we have this compound of phenol. Look at this compound of phenol, trinitrophenol, which is known as picric acid. So this compound is known as acid, but this is not acid. This is a phenolic compound, but this is known as picric acid. Because of this being strongly electron withdrawal by 3 nitro groups at ortho and para position, this becomes very strong acid. In fact, this is stronger acid than that of benzoic acid. So this reacts with sodium bicarbonate So look at this. Simple phenol is very weak acid, does not react with sodium bicarbonate. But if we have nitro group at this ortho and para position, the acidic character of this phenol becomes very more. Since this compound is highly acidic, this reacts with sodium bicarbonate. But otherwise, phenols does not react with sodium bicarbonate. So this is the acidic nature of phenols. Now this acidic nature of phenols can be exploited in number of reactions, like look at this. A reaction with acetyl chloride COCl. When this reacts with acetyl chloride, phenol reacts with acetyl chloride. When the oxygen of phenol having 2 lone pairs of electron act as a nucleophile, so this is attacking electrophilic center and this removes Cl, so this gives you acylation. This is known as acylation of phenol. So the reaction of phenol with acetyl chloride gives you this compound. Acetophenol is formed. Then we have, look at this, a reaction with acetic anhydride. Acetic anhydride this is acetic anhydride. Again, look at this oxygen of phenol having 2 lone pairs of electron is an item nucleophilic side, and this attacks electrophilic carbon, and from this acetic acid is removed. When this gives you acylation of phenol again plus CH3COOH. This is reaction of phenol with acetic anhydride or acetic chloride gives you acylation of phenols. Reaction with benzoyl chloride. Reaction with benzoyl chloride, we have this phenol react with benzoyl chloride. This is similar to acetyl chloride, but we have benzoyl chloride. When look at it, this reacts here, and from this Cl is removed, so we have this benzoyl chloride. So reaction of phenol with benzoyl chloride, benzophenone. This is known as benzophenone. So this reaction of benzoyl chloride with phenol. This is known as Schotten-Bowman reaction. So Schotten-Bowman reaction is benzoylation of phenol with benzoyl chloride. This reaction is known as Schotten-Bowman reaction. So these are some of the reactions in which we have this use the acidic property of phenol. The acidic hydrogen is used to react with the compound. In all this, look at this, hydrogen is removed, so this gives you HCl. So these are some of the reactions in which the acidic property of phenol is observed. Apart from this, we have a number of other reactions also. Second reaction, reaction with zinc dust. With zinc dust. So phenols on heating with zinc dust, phenols are converted to benzene. So phenols on heating with zinc, this gives you benzene. So zinc is acting as a reducing agent, so phenol is reduced to benzene and zinc is converted into zinc oxide. So this is a reducing agent. So phenols on reduction with zinc gives you benzene. So this is one of the methods for preparation of benzene that we can use in laboratory. Reaction with ammonia. Phenols on reaction with ammonia under pressure in presence of catalyst. So we have looked at this reaction of phenols with ammonia in presence of zinc chloride catalyst under pressure. This gives you aniline. So we can use this as a method of preparation of aniline. So reaction of phenol with ammonia, zinc chloride, high pressure gives you aniline. Number 4, reaction with TCl5. Reaction of phenols with TCl5. So phenols react with TCl5 when this gives you chlorobenzene plus POCl3 plus HCl. So if you look at this reaction is almost parallel to that of alcohols. Alcohols react with TCl5 to give you alkyl chloride, POCl3 and HCl. Similarly, look at the phenol, TCl5, chlorobenzene, POCl3 and HCl. But this phenol further reacts with this POCl3. Phenols further react with POCl3 when this gives you this compound triphenyl phosphate phosphate. So further reaction of phenol with POCl3 gives you triphenyl phosphate. So the reaction of phenol with TCl5, the first step there is a formation of chlorobenzene plus POCl3 PuCl3 further reacts with excess of phenol to give you triphenyl phosphate. But if the reaction is with PCl3 phosphorus trichloride, we are looking at this phenol reacting with PCl3, when this gives you chlorobenzene plus phosphorus acid is formed. So these two reaction is parallel to that of alcohols. So this is a reaction of phenols with PCl5 or PCl3, which can be used for preparation of benzyl chlorides or chlorobenzenes. So these are some of the reactions in which OH group of benzene is removed by some other groups. Now, apart from these reactions, there are very important reactions of phenols, which is known as electrophilic aromatic substitution reactions. So this is very important reaction. Electrophilic aromatic substitution reactions of phenols. So look at this, we have this phenol. So this oxide of phenol is having two lone pair which is in conjugation with the benzene ring. Now this electron pair can be involved in resonance with the ring, and this OH group, we say this is ortho or para directing groups. Let's see why this is ortho or para directing group. That means when we carry out electrophilic substitution reaction of phenol, the incoming electrophile will always be directed to the ortho or para position. This is the meaning of ortho para directing group. So the reason being, due to resonance, this resonance, look at this, electron density at ortho and para position is increased, because when we carry out this resonance structure, negative charge appears at ortho and para position. So because of this electron density being increased at ortho and para position, OH group of phenol is ortho para directing group, is a very strong activating group. So look at this, this is ortho position, we have negative charge. Further delocalization gives you negative charge at para position. So again look at this, density, electron density increases at para position, and further delocalization again gives you negative charge at ortho position. So if you look at this resulting structures, electron density at ortho and para position is decreased without altering the electron density at meta position. So this is the reason why the electrophiles are attacking at ortho and para position. So this is because of this resonance. If suppose question says why phenols is ortho para directing in nature in electrophilic substitution reaction, the reason is due to resonance involving electron pairs of oxygen with phenol, the electron density at ortho and para position is increased, and we have to show this resonating structures. And after this will come, hence OH group attached to benzene is a very strong activating group, and which is ortho para directing nature. That means when we carried out this reaction with electrophile, this incoming electrophile, this is always directed at ortho position and the para position. You will get a mixture of this ortho and para substituted phenol, but due to the steric hindrance at ortho position, para compound will be forming as a major product. Steric hindrance. So whenever we carry out electrophilic substitution reaction of phenol, the incoming electrophile is always directed ortho para position because of this resonance contribution. Or we can say, when the electrophile enters at ortho and para position, the intermediate cation form will be more stabilized, means will have more number of resonating structures than when electrophile enters at meta position. So for a particular structure, if the number of resonating structure increases, stability of the species also increases. So the intermediate form from electrophile entering at ortho and para is more resonance stabilized than when the electrophile enters at the meta position. So you can opt either this way or this way. So let's take up some important reactions of phenol. First, look at this halogenation, that is bromination or chlorination. In presence of catalyst, that is halogenation of phenols. So phenols on a reaction with these two, bromine in presence of iron, we can take this bromine or chlorine. When this gives you mono substituted product, we have this Br or substitution at para position. As I told you, this para compound will be forming as a methyl product. If the same reaction, bromine in presence of carbon disulfide or CCl4, bromine dissolving carbon disulfide or CCl4, will get the same product, that is a mixture of ortho and para, and in this para will be forming as a major compound. But if we look at this reaction very carefully, if the same reaction phenol plus bromine is carried out in water, that means bromine dissolving water. So when bromine dissolves in water, we get a compound that is tribromophenol. So look at this reaction very carefully. This reaction is important reaction. So whenever look at this, phenols react with bromine water, all the ortho and para position is simultaneously halogenated. The reason being, bromine dissolved in water gives a very strong electrophile, and phenol, because of this being a very strong electron releasing group, is a very strong activating group. So we have a very strong activating group and a very strong electrophile. So combination of these gives you all the ortho and para positions being simultaneously brominated. The same reaction is also found if we carry it out with chlorine. So in polar medium we have tribromo compound, but in non-polar medium or in presence of catalyst we have mono substitution. Same reaction is also obtained if we carry it out with aniline. Aniline plus bromine, again tribromoaniline is formed. So this is the reason bromine dissolved in water is a very strong electrophile, and phenol is also very strong electrophile and nucleophile in character. So strong nucleophile gives all the three positions to be simultaneously halogenated. Then we have nitration of phenol. Now phenols being very strongly activating group, we can carry down this nitration by nitrous acid. So reaction of phenol with nitrous acid. First we get this nitrosophenol plus we have ortho. I'm just focusing on ortho and para. So nitration of phenol with nitrous acid give you nitrosophenol. Now these nitrosophenol is further oxidized to dilute nitric acid when nitrosophenols are formed. So nitric acid being an oxidizing agent itself oxidize this nitroso to nitro group. So normally look at this, we don't use this dilute nitric acid for nitration, but phenol being very strongly activating group, we use this dilute nitric acid for nitration. In the first step, nitroso compound is formed. So this nitroso compound is oxidized by nitric acid itself. So nitric acid is an oxidizing agent which oxidizes this nitroso group into nitro group. So we can carry down this with dilute nitric acid. But if we use strong nitric acid or concentrated nitric acid, or we have this nitrating mixture HNO3 plus sulfuric acid, which is a very strong nitrating mixture. So by use of this strong nitrating mixture, we get trinitrophenol NO2 nitration at ortho and para position. So with strong nitrating mixture, we get picric acid. All the ortho and para positions are nitrated. But if we use dilute nitric acid, then this mononitration takes place. That is at ortho and para position. So this is the difference between the use of dilute nitric acid or strong nitric acid. So if you look at this is picric acid that we have discussed earlier while discussing the acidic nature of phenols. So by use of strong reagent, we get substitution at ortho and para position. Similarly, look at this sulfonation. So we have looked at this phenol. This reacts with concentrated sulfuric acid, which is used for sulfonation. Sulfonation takes place at ortho and para position. Sulfonic acid group is introduced. So sulfonation takes place at ortho and para position. No further sulfonation is possible. Reason being, look at this sulfonic acid group is a very strong electron withdrawing group. So because of this big electron withdrawing group, this ring becomes deactivated. So no further takes place. But if you look at this compound very carefully, I'll give you some reaction here. Sulfonation reaction is a reversible reaction. We can remove or we can add sulfonic acid to as we require. But if you look at this, we have this. If we start with this, ortho or para sulfonated phenol, if this compound is made to react with bromine in presence of water, so these ortho or para sulfonal phenols, if these react with bromine in water, these remove sulfonic acid group from the benzene ring, and this is simultaneously brominated. So desulfonation takes place followed by bromination, and from this sulfur dioxide gas is released. So this is a very, look at this, we can examine because this is a very strong electrophile. So these first desulfonates and followed by bromination takes place. Instead of this, we can also use acidic group, carboxylic acid. If we use carboxylic acid, then carbon dioxide gas will be released. So these compounds, the sulfonic group or the carboxyl group present in the phenol is first desulfonated or decarboxylated, followed by reaction with bromine to give you tribromophenol. So this is sulfonation. As I told you, is a reversible reaction. We can add sulfonic group or we can also remove sulfonic group. So this is sulfonation reaction of phenols. Then we have Friedel-Crafts reaction of phenols. Friedel-Crafts reactions of phenols. So we have this phenol. Phenols react with alkyl halides in presence of AlCl3. When alkylated phenols are formed, alkylation at ortho position and alkylation at para position. So this is alkylation. So we say this is alkylation reaction. Reaction of phenols with haloalkanes in presence of AlCl3 catalyst. If reaction of phenol is carried out with acyl chlorides or acyl halides in presence of AlCl3, when acylation takes place at ortho position and para position. So this reaction is known as acylation reaction or Friedel-Crafts acylation. So Friedel-Crafts reaction of phenols gives you acylation or alkylation at ortho and para product. But one thing that we have to keep in mind is the yield is very poor. Yield of products is poor. Though phenolic group is a very strong activating group, so we should get a large quantity of the alkylated or acylated product. But the yield of this alkylated or the acylated product formed by this reaction is very poor. The reason being because of the complex section. Because of the complexation of phenol with catalyst, the ring is highly deactivated, means the reactivity is decreased by this complex formation. Now let's see what is this complex formation. So we have this phenol. So phenol, look at this, oxygen is having 2 lone pairs of electrons. So this is a Lewis base. So this combines with AlCl3. So this is Lewis acid, this is Lewis base. So first this forms a complex AlCl3. So now in this process, oxygen of phenol aqueous positive. So because of this positively polarized oxygen or the positive charge on oxygen, this becomes a very strong electron withdrawing group. Due to this electron withdrawal by oxygen, this ring becomes highly deactivated. So because of this deactivation by this positively polarized or positively charged oxygen, the ring becomes deactivated. As the ring is deactivated, the product of alkylation and acylation is poor. Otherwise, the reaction should have been a very good reaction, giving large quantity of the products. So while this reaction, we have to be very specific or very careful. Apart from this, let's take some important reactions, named reactions of this. This named reaction, that is Colby's reaction. Colb's reaction is a reaction of phenols or phenoxide ions with carbon dioxide in presence of base. A reaction of phenols with carbon dioxide in presence of alkali, or we can say reaction of phenoxide ions with carbon dioxide. So in the first step, this gives you carboxylation at ortho and para. So we can look at this because we have a base. So base, phenol being strong is a basic compound. This acidic compound. This reacts with base to give you phenoxide ion. Now this on acidification gives you orthosalicylic acid and para-salicylic acid. This is salicylic acid. So this reaction, the reaction of phenols with carbon dioxide in presence of base, when substitution takes place at ortho and para group, or a carboxyl group is introduced at ortho and para compound to position, giving a compound which is known as salicylic acid. This reaction is known as Colby's reaction. So this is the electrophile. And why we recall basic medium? Because look at this. This base reacts with acidic hydrogen, is converted into phenoxide. So phenoxide is a much more stronger activating group than the phenol itself. So to increase the activating nature of the phenolic group, we use basic medium. And this salicylic acid, if you look at this salicylic acid, so look at this salicylic acid. We have this salicylic acid, orthosalicylic acid. Look at this, carried out this with acetyl chloride. Acylation takes place. Acetyl salicylic acid. Carried out this reaction with methanol. Again, look at alcohol acid, ester will be formed. Methyl salicylate, this is acetyl salicylate. This acetyl salicylic acid, this is known as aspirin. That is the disprin tablet that we take as an analgesic, painkiller जो हम लोग लेते हैं, disprin, that is ये compound. This is known as oil of wintergreen. Now we have a plant which is known as winter kiln. उसमें ये वाला oil पाए जाते हैं, that is acetyl salicylic acid. Sorry, methyl salicylic acid. But if we use this benzoyl chloride, then we have this is known as salol. So means this, so we can use both this for ester formation, both these functional groups. So depending on, we get these different types of compound. That is benzoylation here, acetylation here, so we liquid ester formation here. So this is the importance of this salicylic acid. So from this we can prepare a number of important compounds. So this is called this reaction. Number 6, we have a reaction, this is known as Gatterman reaction. This is a reaction of phenol or phenoxide, with HCN in presence of HCl. So reaction of phenoxide ions with hydrocyanic acid in presence of HCl when aldehyde group or formyl group is introduced to ortho position and para position. So on acidification, this will give you orthosalicyldehyde and para-salicyldehyde. So we have look at this. This is reaction as formylation reaction, because a formyl group is introduced at ortho and para position. So this is salicyldehyde. So reaction of phenoxide ion with HCN in presence of HCl, electrophilic substitution reaction takes place at ortho and para position, and a formyl group is introduced at ortho and para position, resulting in the formation of salicyldehyde, ortho-salicyldehyde and para-salicyldehyde. Now for this reaction, the electrophile is, look at this, we have this HCN. Nitrogen is having lone pair of electrons, so these combines with H plus and coming from this Cl, when this gives you HC double bond and H with a positive charge on these carbons. So this is acting as an electrophile, and on acidification they C double bond N bond breaks to give you aldehyde group. So this is Gatterman reaction. Now इसका एक भाई भी है. So let's see the other reaction. The reaction is known as Gatterman-Koch formylation reaction. Gatterman-Koch formylation. Again यहाँ पे एक formyl group is introduced. Formyl group is introduced means aldehyde group is introduced. As a result, we have reaction of phenoxide ion. These phenoxide ion reacts with carbon monoxide in presence of HCl. So the reagent is carbon monoxide HCl in case of Gatterman-Koch. In case of Gatterman reaction, HCl and HCl is the reagent. And we have formylation at ortho and para position. So same product is obtained, that is salicyldehyde, but the reagents are different. So what is the electrophile here? Let's see the electrophile for this reaction. Carbon monoxide. So carbon is negatively polarized, oxygen is positively polarized here. So this combines with H plus ion. When this gives you HCO positive. So this being resonance stabilized, look at this, let's say when this gives you HC double bond O with positive charge on carbon. So this is acting as an electrophile. So this reacts with the benzene ring to give you ortho or para formylation reaction. So this is Gatterman-Koch formylation reaction. So in this Gatterman-Koch formylation, we have formal group introduced at ortho and para position. Next reaction, that is also a name reaction, which is known as Fry's rearrangement. Or suppose first take up this Rimmer-Tiemann reaction. Rimmer-Tiemann reaction. Now in this Rimmer-Tiemann reaction, we have two types of reaction. We use as formal sodium salt of benzol, phenol. Now this reacts with chloroform in basic medium, or we can take phenol plus chloroform in presence of base, when this gives you formylation at ortho and para position. So if you look at this, in all these reactions, the products are same but the reagents are different. So these on acidification gives you salicylaldehyde, ortho and para salicylaldehyde. The electrophile for this reaction is, we are looking at the CaCl3 reacts with OH minus. So these contains 3 strongly electron withdrawing groups. So these withdrawn electron density from carbon, and this hydrogen is acidic. So this acidic hydrogen reacts with base to give you CCl3 minus plus H2O. So these decompose to give you CCl2 plus Cl minus, and this gives you a very important species which is known as dichlorocarbon. So dichlorocarbon, this is the intermediate formed in this reaction, and this reacts with this phenolic group at ortho and para position, followed by hydrolysis. because जब ये रिएक्ट करेंगे तो we have chlorine compound. So these on hydrolysis gives you diol. So geminal diol being unstable, immediately water removes and this gives you aldehydic group. But in the same reaction, if we change the reagent, that is, if we take this phenolic compound plus carbon tetrachloride, so rather than chloroform, we are taking carbon tetrachloride. If carbon tetrachloride is used, then the products are salicylic acid is formed. Plus para substitution. So this on acidification gives you salicylic acid, orthosalicylic acid, or plus para salicylic acid is formed. So these two reactions is known as Raymond-Tiemann reaction, but with chloroform product is aldehydic group, with carbon tetrachloride product is acidic group. So this itself is the electrophile here. This is the electrophile for this reaction. Then we have this reaction, a reaction of phenol with formaldehyde. A reaction of phenol with formaldehyde in presence of acid. This gives you a polymer which is known as Bakelite polymer. So phenol plus Formaldehyde in presence of acid gives you a very important polymer which is known as bakelite polymer. Phenol formaldehyde resin which is known as bakelite, which is used in switchboards, high quality switchboards. These are made up of this bakelite polymer, that is a polymerization reaction between phenol and formaldehyde, and in this reaction again electrophilic substitution reaction takes place. Then we have some reaction that is known as Fry's rearrangement. This is from phenolic esters phenolic esters. Now these phenolic esters on heating with AlCl3, a reaction of these phenolic esters with AlCl3, rearrangement takes place in which the acetyl group migrates from oxygen to carbon. So this rearrangement is known as Fry's rearrangement. So an acetyl group migrates from oxygen to the carbon of ring. COC3 migrates from oxygen to carbon, from phenolic oxygen to carbon of benzene ring. This rearrangement is known as Fry's rearrangement. Now if you look at this, if the ortho position is blocked, then the reaction takes place at para position. And if you look at this product is favored at low temperature. Low temperature favors para product formation and high temperature favors ortho product formation. But if ortho position is blocked, if suppose we have this ortho position is blocked, if both the ortho position is blocked on the reaction with AlCl3, this gives you substitution at para position only. So no ortho compound will be formed because already ortho position is blocked. So we get para substitution. So this is some of the important reactions, named reactions of phenols, and majority of these named reactions, except for this Fry's rearrangement and the bakelite formation, all these electrophilic substitution reactions that we have taken up in the previous earlier class, that is in the 11th class, during electrophilic aromatic substitution reaction of phenols. So this is simple phenol. Now we have a phenolic compound. Let me give you just small hints about this phenolic compound. Naphthol, we have to put this one naphthol on sulfonation with sulfuric acid, and we also have this 2-naphthol this is 2-naphthol sulfonation of this 2-naphthol. So 1-naphthol at low temperature 80 degrees centigrade, when this gives you sulfonation at ortho, because this group is more reactive because of the presence of this OH group, so activation of this rings takes place and ortho position is more reactive. this ortho position is blocked, so we have this ortho position. It is sulfonation at 2 position. Now this on heating at 160 degree, then this is converted into this is at 160 degree centigrade. Sulfonation days of this so we are looking this being ortho-para-dilating group. Substitution takes place at this position. So this is how we carried out sulfonation of this naphthol, 1 naphthol or 2 naphthol. So this is 1 naphthol substitution at 1 position, 2 naphthol OH group at 2 position. So this is also phenol in which we have 1 benzene ring attached. So sulfonation at ortho position or para position, para compound is unstable because of stirring in exposed by this hydrogen of this phase. So this is the product of sulfonation of naphthols. So these are some of the important reactions of phenols in which we have more focus on electrophilic substitution reaction and some of the named reactions. So these named reactions are important from examination point of view. So please go through all these named reactions. What is a named reaction, reactant, reagent, product, and what is the reaction condition, and if we have electrophile, then what is electrophile involved in all these substitution reactions. So this is all about chemical properties of phenols.